This is like library parsers. So start documenting start elevating. I thought this is where I'm like, I have no idea. It's like if I lower down, then you'll see then I
Hello, 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 hello. This gonna work? Hello, hello. Hello, hello, testing, testing. Hello, hello, hello. Wow. Okay. So no microphone today. Great.
before you saw that. That's what I
Okay, so what are we doing today?
Because like here it says interview on
Here's the outline of what we're going to do today. Today, the last portion of the class is going to be a lecture lab. So please check out OB, which is what you're going to be using in the lecture lab. And then the course recommender is going to be a project that we'll use to demonstrate hashCode and map and data structure. So get those two out of the lectures repository first. So the outline for today is to cover collection classes. So the idea is that, you know, we looked at diagrams like this, and you should be able to interpret this diagram, right? And this diagram has association relationships and composition relationships, and both of those require for you to maintain data structures, right? To remember associations, to remember compositions. And so that will have us go over collection classes in Java. In particular, we're going to talk about lists and sets, but then we'll also talk about maps. And maps are going to use hashing functions, which is this magical hashCode function that I've avoided talking about in the past. But now we're going to actually connect it up with what we talked about last time, which was equals and equals equals. That's going to be the map data structure. Then there's the lecture lab today. And then for the week, we actually have extra DLC hours. We know that you guys are working on the first phase of the project. It's probably taking up a lot of your time, or it should, you know, if you haven't started yet. So the DLC hours, we're going to have an hour on Tuesday, a Thursday, and a Friday hour that you can go in CTAs for some extra help. And then final note here, just kind of a reminder that the midterm 2 is coming. So happy Halloween, everybody. Midterm number 2 is going to be a week from this Wednesday. So that's going to be due concurrently to the second stage of Project 2. So you're going to be juggling a lot of balls, okay? So make sure that the material is sinking in, and then you come see us in office hours, and then you come to DLC hours to make sure to review everything that we've been working on. Yeah?
What is the null pointer exception?
What is a null pointer exception? A null pointer exception. How many of you want to know what a null pointer exception is? Wow. What context is this coming up in?
Tabs base 1.
Tabs base 1.
Context
Quickly. So remember that when we create objects in Java, if I declare a list L, great, and I'll just say list L. Okay. So this list L does not point to anything. Yeah. Right. It's kind of unlinked. So in order for me to actually have it be assigned to an object, I have to create an object. So I have to do something like L equals new array list. Right? So I need the new keyword to actually make sure that L points to something that exists. So until this happens, L is a reference that points off into nowhere. Except that Java usually initializes L to have the value null. pointing to null. So if before you run the statement, before you actually initialize it, if you do L dot, length, for example, which should get you back the length of the list, you're actually calling L dot length on null. So that's a null pointer exception. Okay, so before you use a variable, you have to make sure that's initialized and pointing to an object. So make sure that this is some kind of list. Yeah.
The week of the midterm, we have.
Do you have lab at the week?
Do we have labs?
I think you do have lab because you're going to be working on project phase 2. So you're not going to have anything due in lab. You're not going to be graded in lab. Yeah.
I'm slightly confused about the material that we've done from midterm 1 until midterm 2. It feels like all that we've done was exceptions and a little bit of composition and maybe parsing, but what else have we done since?
We did associations, right? We did the compositions, that stuff. Right, so a large part of it is going to be mapping these relationships to actual code elements. And then we're going to cover a bunch of stuff today, tomorrow, and Friday. We can have a lot more that we can test you on. It's going to be awesome. Okay, let me jump in so that we actually have a midterm and test you on it. So what are the data structures that I'm talking about? So here's this diagram that you guys seen before and is actually posted in the schedule. And this is a diagram of all the collection classes that we want you to know about, except for tree set. So don't worry about this last one, corner tree set. So really there's 3 actual concrete data structures that you should know. And they're organized in the following kind of type hierarchy. So at the very top you have an interface, and it's a collection. And what does a collection support? Well, it's a collection of items. So you can add a new item to a collection. You can remove an item from the collection. And then you can somehow walk across the collection. So you can iterate over the collection. And then the collection gets sharded, it becomes less abstract when you talk about lists and sets. So a list, contains a collection of items where every item has some specific position. So there's an order imposed on your collection. That's what a list represents. And obviously it supports certain operations, like you can add an item at a specific index. Right? Whereas with respect to a set, this doesn't actually make sense. So you can still add and remove items from a set, but there's no predefined order in a set. And then the actual concrete types that you have are ArrayList, LinkedList, and hashCode. Okay, so we're going to talk today about how, what are these different properties within ArrayList, and how do these compare between ArrayList and LinkedList. And then we'll also talk about hashset, which will get us talking about hashCode and hashing functions. Okay? So how many of you know what an array is? Have heard the word array? Ish. So what do you think array is? All of you who raised your hands. Yeah.
Like a list of numbers and essentially a vector, I guess.
Right. So an array is one way to implement the list. And when we talk about arrays, we talk about them in terms of something very concrete in the computer. Talk about them in terms of memory. So an array list represents a list as a contiguous segment of memory. So my array, I typically draw these as these kind of blocks that have partitions in them. So my array will look something like this in memory. And so I can give positions to these elements in my array. So this might be position 0. Computer science, we start counting at 0. Then you'll have position 1, 2, and so forth. 3, 4, 5, 6, 7. Okay? So each of these items here, it's a cell. And since we have a strongly typed language, we know exactly what will go into one of these cells. So if I have a list, integer, And my list integer equals new array list. Integer. Then I know that this array actually contains numbers. Right, so initially I create some list, let's say list L. So my list is going to be empty. And then I can do something like L.add the number 2. And this will change my picture to look like the same array with the same cells, except that number 2 will be in the first cell at position 0. That's my in-memory representation of an array. An array is just, a contiguous amount of memory that was allocated for you to use in your programming language. And so if I do L.add 10, then I'll add 10 at the first position, and so on and so forth. And then when I run out of space, when I get to the very end, I might have a number like 99. If I want to add anything else to the array, then typically what Java, what my programming language will do, they'll support this operation by actually allocating a longer array, one that's longer than the one I already have. And I'll just copy things over cell by cell. So I'll copy over 99 into some cell here, and then I have more space. So if you think about this array, it's this contiguous amount of memory. You know how long each cell is because you know exactly what it's storing. So if it's an integer, it's storing maybe 32 bits or 64 bits. If it's a string, it's storing some number of, well-defined number of bits to represent the string. So here are the set of operations that you might want to carry out on your list. And next to them, there's actually a complexity measure. So how many of you know what big O notation means or stands for? How many of you have seen it? Okay. So there's these things to the right of every operation, right? And there's really only two kinds that are here, that are listed here. And those are O of 1 and O of n. So this is a mathematical notation. It's called a big O notation. And what it's intending to convey is how much time it takes to execute a specific operation. Yeah.
It's an open variable scaled linearly with numbers.
So what we mean is that O of 1 is going to be constant time. So for example, my list.add operation for an array list takes nearly constant time. And what that means is actually adding a new number to my integer array list is going to be constant time, regardless of how large my array is and what it contains. So that operation is going to be fairly fast. And the reason it's fast is because I can compute exactly where the next cell is. So if this is my empty cell, then I know that it's exactly this many items across. Right? So it's the number of cells that I have here times the length of every cell in bits, and then I get exactly the next thing, the next cell where I need to write in my number. So if I want to add something to my list, it's going to be constant time. If I want to add something in the middle of my list, it's O of n, which is going to be, which means linear in length of input. So my input to all of these operations are these arguments like add at position I and add some element E. But another implicit argument is the actual list, because I would have to add that element E to some list. So the length of that list will determine the runtime of these operations. So this n actually represents the length of all of the inputs, including the list. And the list is going to dominate. Right? If I have a very long list, that's going to be much bigger than any item I might have in the list. Or an index. So if I want to add an item into a specific position, what do I need to do? I have to get to that position, like I here. So I have to iterate across. And then I have to change this item to be something else. So all of these operations, like remove, for example, takes O of n, because it also needs to change the size of an array. So if my array was this length, I need to allocate a new array that's going to be the same length minus 1. So it needs to exclude the 99. And then I need to copy them over. So that's also going to take as long as the length of my array. So it's linear in the length of input, but there's going to be some constant. Well, some multiplicative constant. Okay, so you can get this print out of collection classes, and then it's going to tell you what the time is for executing each of these operations. So why would you want to know this? Why is this relevant?
Give you an indication of how fast your program should run.
So you can use this to approximate how fast your program runs. But what's another reason? What's a more important reason?
It shows you what can be practical, like in what situations it would be practical to use which kind of collection.
Right. So that's really the answer I was going for, right? So here, you have two lists. You have an array list and you have a linked list. Which one should you use? So they export the same API. They look identical, right? They're both list objects, list classes. So if you treat them as a list, you get the same API. You can add an element, you can remove an element, right? You can add an element at a specific position. So what's the difference? Why do we have two? There's actually more than two in the library. So the reason you have more than two is because they're implemented differently. So the array list is implemented using an array. So it works as follows. And the implementation has specific properties. Now a linked list is implemented in a completely different way. And because of the difference in implementation, it has different performance. So it supports the same API, which is great because you can swap one out and use a different one. But you have to know ahead of time approximately how you're going to use them if you care about performance. If you don't care about performance, it doesn't matter. Right? They export the same API. So what does a linked list look like? So a linked list is another way to implement the same abstraction. So you want to implement the abstraction of having an ordered list of items. And so the way a linked list does it is not by allocating ahead of time, but allocating on demand. Right? So the array list says, well, I'm going to have a chunk of memory. I'll divide it into these items. And then every time you need to use one more item, I'll figure out how to use it. So array list doesn't do this. So if I define my list L equals new linked list, and let's say again we're storing integers. So my L initially is just going to be this like empty square. Like it contains nothing. Right? There are no elements in my linked list. So my L, it's an object, it's a linked list. It doesn't point to null, but it doesn't have any elements in it. It has very small memory footprint. So if I want to do L.add 1, if I want to add an element to my list, then this L is going to allocate a new piece of memory. It's going to allocate a node, as we call it, and it's going to put the number 1 inside it. And then if I want to L.add 5, then this node is going to have a link to the next node, which will contain the number 5. So the way I build a linked list is I have this chain that runs across my memory. It links the relevant locations into my list. But they're not contiguous, right? They may be anywhere in my memory. So I'm not pre-allocating a fixed amount. So in terms of adding a new element to my list, it's really easy. Because the linked list keeps a pointer to the head. So this is the head of the list. And this is the tail of the list. So I have a pointer to the head, and I have a pointer to the tail. So if I want to add at the end of the list, I just say, well, I'm just going to jump to the tail, create a new node, and then change my tail to point to the new node, and make the link between the two. So in terms of adding, it takes O of 1. It's very efficient. But if I want to just retrieve an item, like get.getAby, then I actually have to walk this entire chain. I have to jump I times in order for me to find the ith element. Whereas in the array, this operation, getI, took O of 1, so it's constant time. Because I just needed to compute exactly how many items I needed to jump to, and then I just jumped. Whereas in a linked list, you have to actually traverse the list and jump I times in order for me to get to the ith location. So a different implementation gives you different performance characteristics, even though they implement the same exact interface, the list interface. So this implementation level detail is useful if you care about performance. Okay, so this is a linked list. Any questions about lists or arrays so far? Okay, let's talk about hashing. So the other data structure on here is the hash set. And a hash set takes a completely different approach to storing its elements. So remember, the array is this contiguous amount of memory. And I need it to be contiguous because I keep things ordered in my list. So I need to somehow remember the order. And in my linked list, I also need to remember the order. And the way I remember the order is by having those links. Right? So if I have a link from object A to B, that means object A comes before B in my list. In my hash set, I don't need to remember any order. I don't have an order in my hash set. It's a set. So it uses a very different strategy for actually maintaining its elements. So a hash set, you can think of it as also like an array. I'm going to draw it vertically here. So the underlying representation is that it also has finite number of cells, and they're all pre-allocated. But the way I'm actually going to assign a position to an element that I store in the set is going to be based on a hash function. So a hashing function, the way to think about this function is that it's, let's say it's h. So my hashing function h goes from some element e to, it goes to something like 0 through n, where I have 0, ... n positions in my array. So my hashing function can assign an element that I give it a location in this array. And the way it does it is doing so almost semi-randomly. So if I have an object like course, which we went over last time, and the course has a department, it also has some number. So let's say I had a course object, so I would say course C equals new course CPSC 210. So this might be an object, and if I want to store it into a hash set, I need to take h of c, and I need to get back an index. That's going to allow me to index into this array. So what hashing function do I use here? It sort of depends on the properties of the data. So the hashCode function that we would define in Java land is exactly this hashing function. So one way in which I can hash things, I can say, H takes a course C, and it's going to give me C.num. For instance, this could be a hashing function. Right, so it returns some number. You need it to be between 0 and n, so maybe what I'll do is C.num, and then I'll actually do modulo n, to do modular arithmetic, and I'll return this number. So it's a hashing function because it returns a number between 0 and n. Right? And it's consistent. So if I give it another course object that's the same, meaning it has the same department, it has the same number, then it'll give me back the same number. Right? Because C.num is going to be identical. So this will assign this course to some position here. Let's say 55. So we'll put this C into this little cell.
And just the way you have it set up now, if you had it in a course in the different department with the same number, would it put it in the same cell?
Great. So good question. So now the question is, well, what if I have a different course? What if I have course, C prime, and it's a new course, but it's in the physics department. So I don't know what the physics is. Maybe Phys 210. So now the C prime has the same course number, 210. So my hashing function is going to return back the same value. The value is going to be 210 mod n, whatever that is. And so it'll also be 55. So that's something we call a collision. So that's a hashing function collision. And the way the hash set resolves it is that when you have a collision, it's actually going to create a little list at this cell. So instead of keeping C like so, it'll actually create a list, a linked list. There'll be C and then C prime. So inside of that cell, it's actually going to have a pointer to all of the elements that hash to this location. That all of them hash to 55. Yeah.
I'm so confused about what C.num mod n does. Why is that?
Yeah, so this is a function, right? It's H. And it assigns an element of some set. So in my case, E is going to be the set of all courses. Right? It's an element of course. And it gives it a number between 0 and n. And this function, it doesn't need to preserve any particular order like we have in the list. So it can give me back any number. And in fact, I want it to give me back a pretty random distribution of numbers. Why is that? Why do we want a uniform distribution?
You won't have one list coming out of there with a whole bunch of them.
Right, so the way to think about it is if this H is a function that's constant, right, it gave me back always 0. Then what does my table look like? It's going to have no elements below 0. And every time I add an element, it's going to add them to the list starting at 0. So I'm going to grow a long, long linked list. So it's going to be a linked list. Right? So my set is actually going to be a list. And it's going to have the same properties as a list. Right? It's going to be fast to add. It's going to be slow to take out, and so forth. So there's a bunch of these list properties that I'll inherit because I bunched all of my numbers to the same cell. So if I uniformly spread out the hashing function, then the length of these lists that I have for each cell will be minimal. Right? Ideally, it'll be just one. I'll have the same utilization as I would with an array. Right? For n elements, I'll have exactly n items. And the great thing about hash set is that addition, removal, containment, they're all constant time. It's really fast to add a new element. It's fast because all I do is I hash the element, I find out what h of e is, and then I jump to that location, and if it's not a list, I just write it in. And if it's a list, I traverse the list, but it's not going to be very far. And removal is the same, right? I compute the hash of the element, and I just remove it from this structure. And then containment is also really easy. How do I check if my course is actually in this table? I compute the hash of C, I jump into the table, and I check if I have a C in that table, in that location. So the hash set is extremely efficient. It's really great, except that it doesn't track order, and its efficiency largely depends on your characteristics of the hashing function. So if my hashing function is constant, you don't get these great benefits, right? It behaves very much like a linked list. Questions? Hashing? We'll talk more a little bit about hashing because we're going to be talking about maps in just a second. And maps are going to be reusing this concept. Okay, so this is our basic kind of 3 data structures. So what's necessary here is you don't need to know the specifics of the big O notation. You don't need to know what it means mathematically. But you need to know that O of 1 is way faster than O of n. Right? You need to know what n actually represents. And then you need to know which one you would choose based on your circumstance. So when would you use a linked list and when would you use an array list? Okay, so that's important. And then the hash set and this hashing function business is really important in order for you to write the proper hash code. Because when you write the hash code method in your classes, that's exactly the hashing function. So let's look at an example of hash code and map with the course recommender. So if you open it up in Eclipse, so what is the course recommender? So here's a small project. It just has 3 files. And my course.java resembles very much what I had last time when we were talking about equality. So it has a string department, it has some number, right? And it just remembers these 2 things. And then I have a course recommender class, which is going to have a map. So a map is a really funny thing because it's a collection that maps object of one type to objects of another type. But in order for this to happen, I actually have to tell it 2 types. So it's not like a list which stores objects of a single type. It needs 2 types. It needs a type for the key, and it needs a type for the value. So when I create a map, I have these brackets, but then in those brackets, I'll actually specify 2 types. So my first type is a course. So this map's key is going to be a course of some sort, and it's the value that is going to map that key is going to be a set of courses. Okay. So the way to see this is that I have a map, and it has 2 parameters, 2 types as input. There's a type K and V. So K is going to stand for type of keys in this map. And V is going to stand for the type of values in this map. And a map looks like as follows. It's going to associate objects of type K to objects of type V. It's going to associate every key to some value. So in the course recommender project, I'm going to have some course. So this might be CPSC 210. that's my course object. And it's going to associate it with the value, and the value is a set of courses. And it's a set of courses that one would recommend for students who've taken CPSC 210. So this might be maybe physics, 327. Maybe it's also going to be biology, 001, and a bunch of things like that. So it's a set of courses. So a map, you usually also call it an associative array because it associates some key with some value. So the operations that a map supports is that you can find out what value a certain key is associated with. So if I had a map kvm, I can say m.get, and I could get it some key k. And this will return some value v. So this will be some k, some v. So for this value of k, it'll give me back this value of v that's associated with it. Okay, so in the course recommender, what does this thing look like? So if I run it, it's a Java app. So it's going to say, enter a name of course for a recommendation, for all. So if I say all, it's just going to list the current contents of this map. So here are all the courses, right? And now we can actually type in the course number to get a recommendation. So what happens if I do this? CPSC 110, I get no recommendation. So that's a problem, that's a bug. Okay, so that's a bug in this project, and we're going to figure out what the problem is. Okay, so first we'll figure it out for this project, and then you guys will look at the second project, the FOB one, in the lecture lab, and figure out what the problem is in there. So to start with, let's take a look at what the course recommender does. So I have my app. So this is the course recommender app class. I have some main. I look at my main as a starting point because that's where the program starts to execute. So first thing that I do is I create a course recommender, and then I'm going to load it up with data. So let's see what loading with data means. So what that means is I'll create a bunch of courses, and then I'll add a bunch of recommendations. So adding a recommendation, if I jump to this thing, it's going to say, well, if my recommendations map, so this thing, recommendations, is the map, course to set of courses. If my map contains a key for this specific course to be taken, sorry, if it doesn't contain a key, right? Then I'm going to create the new set. I'm going to add the course to take to that set, and then I'm going to put into this map, this association. So I'm associating the key, which is the course taken, with the value, which is the course set. And then if I do have the association, if my map already contains this key, which is this block, then I'm going to retrieve the value, which is the set of courses. So that's the get recommendation. That's the get operation. And that will give me a course set. And then I'll just add the one additional course to this set. So in this app, I'm creating all these courses, I'm creating these recommendations, and then in the second half of my main, I'm just going to process commands. So when I process a command, I'm going to read from the screen, right? So this is the line that you see when you run it. And I'm going to create a new course with the department and number that you entered in the screen. And then you're going to say UBC recommended.recommended, and then you're going to give it this course. And if either there are some recommendations or there are no recommendations. So if my courses to take is not null, there's a bunch of recommendations. Otherwise, there's no recommendation. So when I run this thing and I give it the wrong, I give it some course. So for example, if I give it one of the courses that actually exists in my list, Math 180, and there's no recommendation, the key here is that this courses to take is null when it shouldn't be null. So my lookup into this map based on this course number that I gave it somehow fails. Okay? So if I look at my course recommender, this function for recommended, it's simply a get operation from this map. So it tries to retrieve the set of courses that are recommended for this course taken. But for some reason, it's not getting back the course that I want. Right? It's not finding the key, even though the key is actually there. The key is in the map, because the map prints out the set of all keys. So what do you think? What is the problem? I have a map, which is my recommendations. It contains an object, and I print it out. I know that it contains it. But then when I try to retrieve it, when I get taken, even here on line 65, I get back null. Let's go back to the map view. So map associates a key with a value. But how does it actually map this key to this location? Right? It's going to be exactly this hashCode method. So in order to map this key here, you're going to evaluate hashCode on this key. When you evaluate that function, it's going to tell you exactly the cell where you need to write that key k. So if my hashCode function, so if I have k and I have k prime, and they both represent the same course, CPSC 210, I need it to be the case that hashCode of k returns the same thing as hashCode of k prime. You guys remember the equals equals and the equals method? Thanks from last course, last lecture. So this guy was comparing instances of objects. So it was comparing references. So it was saying, are they actually pointing to the same object? Right? Do you have another pointer to a list, or do you have another object? And then the equals method was something that you could use and override to change the behavior, the default behavior. So the hashCode function has the same issue. The typical hashCode that's in the object class, the most advanced, the most abstract supertype. This hashCode thing just returns the reference to object k prime in this case. So if you have a hashCode that returns a reference, then if my k and k prime are two different objects, then they'll be assigned to different locations in this map. So my hashCode of k prime will return a different location. Okay? So the problem in this code is that this course object, this course class, doesn't have an equals or a hashCode method. So it doesn't override them. So it's using the default hashCode and equals methods. Which means that this behavior is exactly what happens. When you run hashCode on K and hashCode on K prime, you get assigned to 2 different locations in your map. So when I ask for it to print out the recommendations for CPSC 210, it prints out nothing because it jumps to a different cell, the incorrect cell in my map. Okay, so if I add my equals and hashCode methods, which is the source generate hashCode and equals things. And if I generate hashCode and equals to use the department and the number of the course, just as before, then Eclipse creates this new hashCode function. And so if I run my program now, and here's the list of courses, if I ask for CPSC 210, then it'll actually fetch and print out the recommendation which matches that object, which it creates. And so in order for that to work, you need the hashCode method. That's overrated. Okay, so I spent a little bit too long on this. So in the remaining bit of time, take a look at this lecture lab. It's going to require you to check out the FOB project. Okay, and the FOB project has a test that fails. It fails in a very similar way, where it has something to do with the way the hashing works. Okay? So why don't you start on it in the next couple of minutes that we have left. And then I can walk around and you can raise your hand if you have a question.
Yeah, I'll just show you what
No, I mean like during.
I mean,
Like, you, I don't know.
because like for me, like
Well, that's only for Facebook. Like for Facebook,
I bring some to check this out, like check this lecture. And it was like so nice. The community was like amazing. I did like there's something called like a fake. It's like fixed paper or something. Or some shit you kind of like no, not even that. It's something that you like inhale. Anything that's cold, like plastic. Yeah. Have a good night. There's like no point in me talking to you. You have nothing to offer. No, it's true. Like, you're just like, I already did. Oh, me too. Like, I would pick my own ass if I saw myself 60 years old. And I'll probably get myself down when I'm You don't remember. It's hard to just shave yourself off. Okay, so yeah, I have one of the functions I have the cursor done, I think. It could be totally wrong. It could be entirely wrong.
Like stops is a flow update stops, and then when you check first, all the stops, and then comparing stops to I did all my work inside my browser. You can do that with
Amy.